So this is my third talk, 3 days in a row at 4:30. If you're starting to get tired of me, I can understand. I'm gonna talk mostly about unsupervised learning, but I'm gonna start with a small parenthesis, which is actually prompted by something you talked about, which is this really cool idea, and it's because we're at IPAM and there are mathematicians in the room, and I think this is a kind of an interesting thing to explore. So there's one thing I've been working on and wrote a couple papers with some of my students a while ago. This was suggested by an informal discussion I had with Gérard Benarous, who is a random matrix theory probability guy at Courant. He was a former director of the Courant Institute, actually. And it's the idea that if you have a matrix, particularly a unitary matrix in complex space or orthogonal matrix in real space, there is a conjecture that if you approximate the matrix, so you can always decompose a rotation matrix by a bunch of 2x2 rotations. You have order n squared of those 2x2 rotations. The physicists call that Givens rotations. So there are little matrices like this, and you take all pairs of coordinates and you kind of rotate them in a particular way. You can basically decompose any rotation this way, or any essentially any orthogonal matrix. But there is a conjecture that if you take the space of all rotations and you take a subset of them, so they are the ones that are representable not by using all pairs of coordinates, but only pairs that are arranged along like an FFT-like graph, right? So you take the nearest pairs, and then the second nearest pairs, and then the fourth nearest pairs, and then etc. So now you have n log n 2x2 rotations. The space of rotations you can attain using this is kind of dense in the space of all rotations. This is a conjecture, it's not a theorem. And we set out to test this because that would be very interesting if we could parameterize, essentially approximate any rotation we want sufficiently close, if we could approximate them with sort of n log n elementary rotations. So first of all, decomposing rotations this way, or orthogonal matrices or unitary matrices this way, gives us a way of parameterizing unitary matrices. So by you basically just have one parameter here, which is the rotation angle, and what that means is that you can use this in a neural net, for example, and do gradient descent in the space of those elementary rotations to kind of identify particular rotations. So the idea that my former student Michael Mathieu and I had was to essentially parameterize Hessian matrices this way, because the idea was to approximate the Hessian matrix of neural net, so we could do kind of second order optimization, and you can decompose a Hessian matrix, which is always symmetric, by a rotation times the diagonal times the rotation inverse, right, which is also the transpose. So you can make this if you approximate the rotation by an n log n matrix, you now have a full Hessian matrix that's approximated by n log n times diagonal times n log n, which would be kind of cool. And you can invert it trivially, right? Because in this factorized form, the inverse of it is simply the transpose, the inverse of the diagonal terms and the transpose of the rotation. So that would be a really great way of maybe approximating second order methods for neural nets. So that turned out to be complicated, but one thing we could do was figure out if we could take a random matrix and see how well we could approximate it by this kind of approximation. So pick a random matrix, feed a bunch of vectors to them, and then use that as a training set to train a matrix parameterized this way. So this would be a symmetric matrix, right, that we try to approximate. And see if you can train the symmetric matrix parameterized this way by rotation, diagonal, rotation, transpose, and how close you can get. And the answer is you can get quite close. So if you train a matrix of this type using gradient descent, and you have to use a bunch of tricks, in dimension 64, so you have a 64 by 64 symmetric matrix, positive definite, and you approximate it with this parameterized factorization, and you take a random vector, you run it through the original matrix, and then you run it through the approximation. The angle between the two rotated vectors is about 35 degrees. It looks like a lot, but in 64 dimensions, it's actually not a lot. So there's a significant positive dot product between the two. So does that mean you can approximate any symmetric function by this? Not entirely clear for practical purpose, but it's kind of interesting. So we wrote a paper, we submitted to a conference, it was soundly rejected, we put it on archive. And we figured out if we could accelerate learning of neural nets with this, and we could, but it's not, it's kind of a little difficult to do the experiments, a little involved. There was all kind of numerical problems and stuff. And then I kind of talked about this story to a group at MIT who was interested in optical implementations of neural nets. And in optics, you can easily implement unitary transforms, essentially. It's very easy because it's reversible. It's kind of like quantum computing, right? A quantum computer basically takes a state of the computer and then multiplies it by a unitary matrix. That's all it can do, in fact. So this idea of unitary matrix is kind of interesting. It has the advantage also that when we backpropagate gradient through a unitary matrix, it doesn't degenerate because it's basically the inverse of it. So backprop in a unitary network, if you want, is like inverting. It's exactly the same thing. So I was discussing this idea with these guys, and they say, oh, maybe we could train a recurrent net using this parameterization of rotation matrices, so that you build a recurrent neural net, and you parameterize the matrix of this recurrent neural net as kind of a linear arithmetic, which is kind of the name people use for this. So kind of n log n product of 2x2 rotations. And what you get is a kind of cheap way of parameterizing recurrent nets, and they seem to be working quite well. And of course, there is no problem of vanishing gradient because the whole thing is kind of invertible. So of course, you have nonlinearities, which put a little bit of monkey wrench in there, but it's okay. So this is kind of a paper, I think, by Rajowski called the Unitary RNN. And this was an idea that Yoshua Benju and I had many, many years ago, but we could never make it work. And so this is a version that actually works with Yoshua Benju and Martin Rajowski, who was an intern with him. And this is this parameterization of unitary matrices. So this one used the n log n parameterization. This one used the full parameterization, the sort of n squared. And what you see is that the performance, when you go to n log n as opposed to when you use the full parameterization of orthogonal matrices is basically the same. I mean, it doesn't make much difference in terms of performance, and it works the same as the other things that people have done using unitary transforms, including, and it works better than STM, and has very fewer parameters essentially. So this was a short parenthesis. Now I think there's interesting connections there with quantum computing and stuff like that. So I don't know where that goes, but sort of an interesting avenue perhaps. Now on to unsupervised learning. So in the various talks I gave yesterday and the day before, I talked about the reason why we need to work on unsupervised learning. There's many reasons why you need to work on unsupervised learning. The first one is there is a bunch of highly interesting applications for which we can collect lots of data, and it's economically feasible to pay people to label it. So things like image recognition or speech recognition or various text applications, translation, etc. But there's a very long tail of applications for which we just don't have, it's not economically feasible, or we'd like to apply those methods to other things, or there's a lot of applications, for example, in biology and medicine, where the size of the training set is very small, so you'd like to pre-train your model as much as you can on unlabeled data, which may be abundant, and then only fine-tune it on whatever labeled data you have. And then there is the main reason why I'm interested in this, which is, we need machines to be able to build models of the world, and this is kind of a form of unsupervised learning as well. The difficulty of this being that unsupervised learning systems, those predictive models, have to handle uncertainty, and that's really what unsupervised learning is all about. So unsupervised learning, in general, you could view as the idea that a system is given a whole bunch of variables at multiple times, let's say. So imagine the vector of all variables, all observed variables that the system has, and all the past values and all the future values, right? And we are at a particular time, and what we ask the machine to do is predict the value of all the variables it does not currently observe, right? So the past variable are not very interesting to infer unless you've not seen them yet, okay? So if you get to a situation, you get into a room, you've never seen that room before, it might be interesting to know what happened before, so you might want to infer what happened before. You get into a room, you don't get a complete observation of all the objects because there are occlusions, so you might want to complete the observation and sort of, feed all the things you don't see. So currently I don't see the front side of this lectern, but I can see it if I go around. So eventually I see those variables, and so I could use a learning algorithm to kind of train it. I don't necessarily know the geometry of this room, but if I move my head a little bit, I might get parallax that will give me some idea about the geometry. And of course, if I wait a little, I know what will happen in the future in this room. So I can get a huge amount of supervision. The problem, of course, is that all the predictions I'll make are uncertain because I don't have a perfect way of predicting the future. I don't have a perfect way of dreaming up what the back of your heads look like. So the main issue of unsupervised learning is, compared to supervised learning, is twofold. The first one is you have many, many more variables to predict. It's actually threefold. The first one is you have many, many more variables to predict, and that's a good thing. The second one is those variables have a lot of uncertainty attached to them, in a sense that you cannot make exact predictions about them. So whenever you observe the future, you might make predictions that are slightly wrong, and there was no way you could make a good one. So how do you train a system in these conditions? Right? And the third one is you never quite know which subset of variable you have access to and which one you're supposed to predict. So you need to be able to predict everything from everything else, but you don't know in advance, unlike in supervised learning, which variables you know and which variables you don't know. Okay? So that's what differentiates supervised learning from unsupervised learning. Other than that, you observe values that you need to predict, so it's kind of like supervised learning, really. So that's the problem of prediction under uncertainty, and it's the fact that there are no perfect deterministic dependencies in the world, and if your world consists of two variables and you observe those two variables, if I give you a particular value for y2, there's two possible values for y1, and you have to have somewhere representing the either the distribution or the set of possible values, or some way of kind of representing it. And if you ask the system for one particular prediction, when you give it the value of y2, the value of y2 is equal to that. If it gives you this, and the world happened to kind of produce that, it's not technically wrong, right? It had no way of predicting. So how do you handle this learning-wise? So one way to do this is, of course, there's one way that doesn't work, which is to train a neural net to see y2, for example, and then predict y1, because a neural net predicts only one value, right? So that doesn't quite work. So one possible way to kind of parameterize this kind of learning is what I call energy-based learning, but it's a slightly more generalized form of probabilistic learning, where you're going to train a machine, and this machine is going to be a contrast function, let's call it an energy function, that's going to give you low values for stuff it observes and higher values for stuff it doesn't observe. Okay, so let's imagine our learning machine is just a box that takes input vectors, let's call them y, and it produces a single scalar value, and that scalar value tells you, yeah, y looks genuine, or y looks impossible, or implausible, and that's a contrast function. There are many contrast functions that will work for a particular situation, like this, for example. So here we have a quadratic relation between y1 and y2, and this contrast function or that contrast function will both capture the dependency between y1 and y2. So a learning algorithm will train this contrast function to basically take the right shape, right? So here is one that's learning, right? These are the training samples, and how do we make sure that this contrast function sort of takes, initially maybe is flat and takes kind of higher values outside. So if we have a parameterized function that computes this thing, it's easy enough to make it take low values on the training samples. You just show it a training sample and tune the parameters so that the output goes down, very easy. But how do you make sure it takes higher value outside? That's the hard part. And in fact, so if you're a probabilist, it's easy. You say, oh, well, this energy function is just a log of a probability. which I can compute with a Gibbs distribution. So here is my energy. I took exponential minus some constant the energy normalized by the integral over the entire domain, and that gives me a probability distribution of y given the parameters. And so then I do maximum likelihood, which means I minimize the expected negative log of the probability of all the data points given my model. And the result of this will be to push down on the energy of the points that I observe and push up on the log of the exponential, the log of the sum of the exponential of all the other points over the entire domain. The problem is that you get an intractable integral in there that you have to approximate with either variational inference or sampling, and that sucks. So people have tried to come up with a whole bunch of alternative ways of pushing up on the energy of points that you don't observe. And there is a whole catalog of them. I'm not going to go through all of it, but you can sort of reformulate classical unsupervised learning algorithms in those terms. So for example, the first thing is to build a machine in such a way that the volume of stuff that takes low energy is fixed, or at least upper bounded. And PCA, k-means, gas and mixture model, square RCA are all of this type. So k-means, for example, k-means you say I have k prototypes. I can place the prototypes where I want. My energy function is a square reconstruction error, which means the square of the distance of a particular point to the closest prototype. Okay, so it's the min of a bunch of quadratic balls. And so I only have k prototypes, and so the volume of stuff that can take low energy is limited, and therefore automatically wherever I place those prototypes, everything else is going to have higher energy, right? And so k-means implicitly kind of regularizes the volume of stuff that can take low energy this way. In fact, this is what it looks like. So this is the energy function for k-means, where z is constrained to be a one of k code. It's got one component equal to 1, all the other ones to 0. This is the prototype matrix. And when you find the vector z that minimizes this reconstruction error, which means which prototype is closest to the data point, you get an energy function that looks like this. So here's a bunch of data points. So I mean, these are a spiral from which I sample data points, and I train k-means to approximate this. And the prototypes are those kind of dark areas here, and they kind of describe this this nice spiral here. So that works really well. Unfortunately, it doesn't work so well in high dimension because you need k being very large and all that stuff. This is what PCA does to you. So PCA can be formulated in this way as well, where in PCA, the volume of stuff that can take low energy is limited to a linear subspace of the entire ambient space. And so you will get low energy for things that are on the principal component subspace, and then anything outside of it will have a quadratic growth of the energy function, which is just a reconstruction error in this case, right? Right. So let's go back to this list. So another set of techniques, which is the probabilistic approach I was mentioning, is the idea of pushing down on the energy of all data points and then pushing up everywhere else. And the everywhere else is kind of the annoying thing where if your ambient space is very large, you don't know how to push up everywhere else unless your energy function is very simple and you can have a closed form solution for it. Another strategy is push down the energy on data points and push up on chosen locations, well-chosen locations, outside of the data manifold, or the area of where you have data. And there's a whole bunch of methods to do this. Contrastive divergence is one of them that is used for Boston machines. Ratio matching, nose contrasting estimation, minimum probability flow. And things like adversarial training is actually in that category as well. So adversarial training is the idea that you train a generator network to generate points that are outside of the manifold of data. And this generator gets better and better as the energy function trains itself. There's a bunch of others that I'm not going to go into, but one that's kind of really interesting is using a regularizer that limits the volume of space that can take low energy. And this is essentially what sparse coding, sparse modeling does, as well as something called sparse autoencoders and predictive sparse decomposition, which I'm going to talk about in a minute. This is about the intractability of the probabilistic approach. Okay, so the decoder-only approach, so there is an example of this is the GLOW system that, or algorithm method that Arthur just talked about. But a much simpler version of it is just sparse coding. So sparse coding, you have the sort of generalized sparse coding if you want. The code, the latent code, reconstructs the observation through a decoding function. And you do this by finding the code that minimizes a reconstruction error plus some sort of regularization term. So in sparse coding, it's just an L1 norm. And so you have two terms in the energy function, which are symbolized by those green boxes here. If your decoder is linear, then, if Z is constrained to be one of K code, as we saw, we get K means. If Z is kind of a computed as kind of a greedy incremental method, then it's just pursuit. KSVD is kind of another way of seeing this, and sparse coding is kind of a way of minimizing this sort of L1, L2, using various methods. And you get, representation energy functions in this space that are an approximation of the data with linear subspaces, basically, right? So that's typical energy function you get with sparse coding. And so I was going to talk about GLOW, but Arthur talked about it, so it's great. I'm not a co-author on this. This is interesting work. So essentially, the idea is, as he said, is it's exactly this model of sparse coding or matrix factorization if you don't have any constraint on Z. But the decoder now is allowed to be a whole neural net, essentially, instead of just a linear thing. And it's a little complicated when if you want to put like a sparsity constraint on this, because now the decoder is going to want to get really large, right? So you're going to have to limit its gain and stuff like that. So there is sort of things that people are playing with there. And Arthur showed like amazing image generation with this. But here is something else I want to talk about, which is sparse autoencoders. So the problem with it's not a problem, but an issue with GLOW and sparse coding is that inference is slow because you have to do this L1, L2 optimization. So one thing you can do is you can build a neural net, essentially, let's call it an encoder, that makes a prediction for what the latent variable should be. And really the inference algorithm minimizes now three terms. One term is how good the reconstruction is. Another term is how sparse the latent variable is, or whatever it is that regularizer you want to use here. And a third term is how far away this variable is from whatever this encoder was predicting. And what we're going to do is train both the encoder and the decoder simultaneously so as to minimize the sum of those three terms. Okay, so that's kind of the energy function, and it's also our objective function for learning. The reconstruction error, the prediction error, and the regularizer on the code. There was an early paper on this called Predictive Sparse Decomposition that we submitted to something like CVPR or NIPS, which was rejected, and we took 2 years to put it on archive. So, but it's from 2009. And only the following one was published in 2010, which was basically the convolutional version of it. And so this is what I'm going to describe. So this is similar to something Michael Elad was talking about yesterday. Convolutional sparse coding, basically, except there is an encoder that predicts, gives you a guess as to what the value of the latent variable is. So, regular sparse coding, you have an L2, L1 cost function with a kind of a linear operator on the latent variable and a kind of a sparsity term. Convolutional sparse coding is the same thing, except you replace this operator here by a bunch of convolutions. So you sum over convolution kernels, the result of a convolution with a feature map. So you have those feature maps, you have convolution kernels, you convolve each convolution kernel with each feature map, you sum up the result, and that's your reconstruction. And this trick was used by us in this PSD, but it was also used by Ziller, Taylor, and Fergus in their CVPR 2010 paper in what they call a deconvolutional network. So it's kind of a stack of convolutional sparse coding. So this is very similar to what Michael was talking about yesterday. And And so the cool thing about convolutional sparse coding is that you don't need to have displaced translated version of every basis function. So here, this is the non-convolutional version of it, where you have, essentially the same basis function at various kind of register position in the window. Whereas if you do it convolutionally, you only need one copy of it because you have all the shifted versions in the convolution in the first place. And so what you get is much more diverse filters. You get those weird endpoint detectors and crosses and things like this, and gratings, which you don't get otherwise. So these are examples of filters that you get with this technique if you train with 1, 2, 4, 8, 16, 32, and 64 filters. And the you have two blocks of almost identical filters. I think the one on the left is the encoder, and the one on the right is the decoder, and they end up being very similar. So the encoder is almost linear. It's basically just a one-layer neural net with a nonlinearity. The decoder is linear. And the filters end up being very similar. Now the next idea, and I'm doing, I'm going back a while back, is the fact that making the encoder a single-layer neural net is kind of crazy because we know that the result of sparse coding, the guess of the value that we should produce for the sparse code, should be the result of something like a sparse coding optimization algorithm. So having this approximated by just a single layer neural net is crazy. My former postdoc, Carol Greger, got this idea that somehow you could, so the problem with sparse coding, of course, is minimizing this L2, L1 cost function. And a popular algorithm for this is ISTA, iterative shrinkage and thresholding algorithm. But Carol's idea was essentially to turn, and a few people mentioned this before. I think Joanne mentioned this in his talk, and etc. And the basic idea there is to reduce lista to a sequence of very simple steps. So for particular definitions of W and S, this is the lista algorithm. Take the input, multiply it by a matrix, shrink the result using a pointwise shrinkage function, then multiply the result by a matrix, add to the previous result you had, shrink and multiply and iterate this until it stabilizes. And that's the ISTA algorithm. And Carol's idea was to say, well, why don't we view this as a recurrent neural net and we let W, E, and S be learned so as to approximate the solution of the L1, L2 optimization algorithm as quickly as we can, as well as we can. And the amazing thing about this is that this works really well. So this was a paper at ACMR 2010. I think the idea has been picked up by the other Bornstein. I have a hard time telling you apart, but I know this is the other one. And some further work, and Pablo Sprackman also, when he was working with Guillermo Sapiro, used this technique for all kinds of stuff. And I think it's a very general class of ideas, which is if you have an optimization problem, or even if you have a PDE, and it's a little expensive, or it takes a while to converge, or whatever, maybe you can train a neural net of some kind, a recurrent neural net perhaps, to give you an approximate solution very quickly to it. And it sounds like a free lunch, but it's not really a free lunch because the reason why it might work is that the type of data that you are interested in solving with those things is usually very structured. Like here, we're trying to reconstruct natural images. It's not the set of all possible random vectors. It's just patches of natural images. And so it could very well be that there is a set of matrices, W, E, and S, that actually does a better job at approximating the solution of the sparse coding problem in that subspace of all possible vectors than the general algorithm ISTA. And that turns out to be the case. So you take this recurrent neural net, you unfold it in time, the number of iterations that you want, and then you train it with backprop to give you the best approximation to the sparse coding problem that you can. And again, you can apply this to basically every optimization algorithm that you can formulate in terms of an iterative algorithm with sort of, relatively continuous differentiable stuff. And this is, here's an example here of finding the sparse coding solution, and this is the reconstruction error, where here for the blue points are 4 over complete basis, and this is the y-axis, the reconstruction error, the x-axis is number of iteration of the algorithm, and this is the error you get with ISTA, or the fast version of ISTA, and this is the error you get with this trained ISTA that we call LISTA. I guess you mentioned this also, Michael, in your talk, LISTA idea. Yeah, let me skip this. Okay, now let me move a little bit ahead. So I talked about this kind of encoder-decoder idea for autoencoders. What I'm going to talk about now is another idea which is more applicable to prediction than reconstruction. It's called error encoding network. This is a paper we put on arXiv in November. It was submitted to ICLEA and rejected. But I think it's a cool idea. I mean, the experiments maybe need a little more work, but the idea is very cool. So here's the problem we're facing. As I said before, the problem of unsupervised learning is you have a set of variables you observe, there's a set of variables you need to predict. Let's say they are the future state of the world or something like that. And there are kind of latent variables that you cannot observe that will determine that future, right? So for example, you observe someone playing a video game. Let's say playing, the lunar lander, right, or the air taxi or whatever. So this little game where there is a little spaceship that, is above a landscape, and if you don't do anything to the spaceship, it kind of follows a parabolic trajectory and kind of goes down, accelerates with gravity and eventually crashes, right? But when the player plays, hits the thruster, the thing is going to kind of decelerate and maybe go up. There are thrusters also to go sideways. And so just by observing, roughly you have an intuitive notion of Newtonian mechanics, and you observe this person playing this game, you can infer what their action is by just looking at how the spaceship moves, right? So somehow you have some latent representation. You can infer what action is being taken for the system. And that's the part that's really not predictable. Like, you don't have a complete model of the player, and so you can't predict what the player is going to play, or maybe you can to some extent. But you can predict the dynamics that the system would have followed without any action on the part of the player. So the idea of error encoding network is exactly that. Let's try to predict the future, but the way we're going to handle the uncertainty about the future is by having a latent variable that represents the action, or whatever latent variable that we don't observe about the future. So we're going to have two modes in this predictor. So let's say we're going to predict the future. X is the past. Y is the future that we eventually observe, and Y prime is the prediction for what the future is going to be. And at first, it's just going to be a deterministic predictor. So we're going to set the latent variable here to 0. Okay, this is a switch that can go here or there. We're going to set it to 0. And we're just going to run this thing through the encoder-decoder. And this encoder-decoder is just going to do the best it can to predict, make the best approximation possible of what the future is going to be. And of course, the future can be a number of different things. And so the best thing that this system can do, if you use mean squared error, for example, is to predict an average of all the possible futures. Okay, so if you're trying to predict an image, it will produce a blurry image that is the average of all the possible futures. If you predict the position of a spaceship, it's going to predict all the possible position of the spaceship, after a small amount of time, depending on the actions that are being taken. So that's what you train the system to do by default. And then you turn the switch to this. This is another neural net that you're going to train. The dimension of Z needs to be kind of restricted, or the amount of information in it needs to be kind of constrained, a little bit like in autoencoders or sparse autoencoders. And what you're going to do is tell the system, learn a deterministic function, so that this deterministic function, just looking at the error in the prediction, is going to predict what the latent variable should be that will make the error 0. Okay? So by just observing the error between the prediction and where the spaceship is now, you can induce normally what the action of the player was. Okay, and we're going to train a neural net basically to predict what the action was from this error, from this prediction error. Okay? So that's what this kind of second phase of training does, where it trains this phi function, by sort of trying to guess what this variable is, so as to minimize the reconstruction error now. And it kind of works, sort of. So this is a small animation where, so you don't see the interesting thing at the moment, but there's a video that was put out by a bunch of people at Berkeley, at the Bear Lab, where they put an object on a table like this, and they have a robot that randomly pokes the object in a random direction. And so what you see here is the initial image, and there is lots of examples of this object being kind of moved around, and you're not being told the action of the robot, or at least we don't let ourselves using it. And what you see here is various image generation that are the result of taking this original image, running it through the predictor with a random value of z, and then generating an image. And so what that tells you is that the latent variable has figured out, the only thing that can happen is that the object can move just a little bit and rotate maybe, but otherwise can't jump to the other side of the of the field, and basically different values of z will produce sort of different results of poking this object, so it moves a little bit. There are other examples that are kind of less, they're not like video things, they are like video games and stuff like that, which I'm not showing, but that's interesting. How much time do I have? Okay. So another work, which I'm not involved in, this is people at Facebook in Paris, is something called failure networks, and it's a very interesting trick that is based on adversarial training. And the idea here is, what if you want to train an autoencoder on images, like faces, for example, but you know that certain faces have been annotated. They are, it's a face of a woman, maybe she's smiling, maybe, she has long hair, she's blonde, things like that, right? So there's a number of labels that you might know about this person. And what you'd like is you'd like to train a system to essentially be controllable so that you can change those known labels and produce an image that is transformed from an original image. And so the way this is done here is you take an image of a person, you run through an encoder, you run through a decoder that generates a new image. And so far so good, that's just an autoencoder, no problem. But then what you do is you put an extra set of variables here that contain the labels that you know. But then what you need to do is, so now it's this complete code here that is going to be used to reconstruct this face. But what you like is, you would like this part of the vector to not contain any information relative to those labels, because you want those labels to uniquely control what this thing is going to do. And of course, you don't have a version of this lady with blonde hair or with or not smiling. You just have one picture of that lady, right? So you put the labels here, and then you're going to have to find a trick to eliminate the information from this part of the code that is relative to those labels. And that's really the key idea in the system. So what you do is you train a discriminator, another neural net, adversarially, and you train it to predict those labels, okay? And you backpropagate gradient through this, and the encoder trains itself so as to produce variables that prevent this guy from actually predicting the label, okay? You can do this with gradient descent, right? So it's kind of opposite to training a classifier. You train a non-classifier, an anti-classifier. You train something to produce a representation for which you cannot actually do the classification, right? Which is kind of fun. And so that eliminates the information relative to the labels from this part of the code. And so you train this with all kinds of different faces that have been annotated. And then in the end, you can change this guy and then produce an image under your control, essentially. So these are examples where the original image is at the top, and then by changing the gender, the gender variable, you turn this lady into into a man. You can add glasses. You can make her eyes more open. You can make her older and open her mouth. And you can do this with everybody. You know, turn this guy into a lady, etc., etc. Or of course, you can sort of, you know, kind of tweak a continuous variable where you have the original somewhere in the center, and you make this lady younger or older. I guess it's easier to make this lady younger. And this gentleman, you know, more male or more female, or, you know, etc. So that's pretty cool. And that's, you know, one of the magics of adversarial training, which, you know, again, we don't know how to measure the performance of it, but as Arthur was saying, you know, it works pretty cool. Last thing I want to talk about, no, I don't want to talk about that, is this, and I'm probably in minus 2 minutes now, but is something called adversarially regularized autoencoders, which is the second paper we submitted to ICLEAR and got rejected. There's 3 submissions to ICLEAR with my name on it. All 3 were rejected, and I'm the chair of the conference. So that tells you I'm not the program chair, I'm the general chair. But what that tells you is that the reviewing process is you know, not biased. or if it's biased, it's not in the direction of, you know. So the idea, the problem here is how do you use adversarial training with discrete data? So adversarial training works really well when you want to generate images, which are sort of continuous spaces. But if you want to use it to generate text, it doesn't quite work. And again, there is, and so that's one statement. And then the other statement is, when we train those autoencoders with sparsity, the reason why we want a sparsity constraint on an autoencoder is because we don't want it to run just the identity function. That's not very interesting. And so the reason we put a sparsity constraint in the middle, or in the case of rational autoencoder, we put some noise on it, is because we want the system to have a limited amount of information that it can store in the code so that it doesn't reconstruct everything, it only reconstructs the stuff we train it on, and it produces high reconstruction errors for everything else. And that is the idea of, the general idea of unsupervised learning, where you want a contrast function that has low energy for stuff you train it on, high energy for everything else. So here the idea of adversarially regularized autoencoder is that you have an autoencoder, and the way you're going to regularize the code is by making it match the distribution of a random variable that you know, with an entropy that you know. So you're going to have a random vector here that you draw from, say, a Gaussian, run it through a bit of a neural net. It's going to produce a variable of the same size as this guy, and you're going to train a discriminator to basically discriminate between this, you know, samples from this distribution and samples from that distribution. And using the backpropagated gradients, you're going to train those 2 distributions to be essentially the same. Okay? But this guy also has to keep reconstructing. So what you have now is a constraint on the code so that its information content is limited by the entropy of that random vector. And then you can use the generator, run through the decoder to actually generate samples. So these are this thing trained on MNIST, and these are generated samples by drawing a random vector, Z vector, and running it through the generator and the decoder. And this is interpolation in this latent space where, you know, you can continuously change from one character to another. But it's more interesting for text. So what if you use an autoencoder for text? This is a conventional autoencoder applied to text. You can use it to generate text. So this text is kind of, you know, mildly correct. Better than if you use a pure autoencoder. A woman preparing 3 fish. A woman is seeing a man in the river. There passes a woman near birds in the air. Kind of weird. Some 10 people is sitting through their office, not grammatical. So, you know, this kind of stuff. But the funny thing is interpolation. So take a random vector in Z. It produces a sentence, not necessarily a correct one. A man in a cave is used an escalator. And then take another point and then interpolate between the 2, and it kind of smoothly transforms the first sentence into the second one. Okay, so I'm going to stop here because I'm completely out of time, and thank you for your attention.
Thank you.
again.